I was invited to make a presentation at the Society for Brain Mapping and Therapeutics on the topic of the biophysics of traumatic brain injury and the integration of magnetic resonance uh, imaging with EEG, as well as new advances in neural imaging. I did this presentation on March 5th as part of the Friday um, seminar series. But it was not recorded. And after I did make the presentation, a number of people have asked if it had been recorded. And so as a consequence, I've decided to redo it on today. It's Monday, March 8th, for those who may be interested in hearing this talk. So I'm just going to begin now with the initial presentation. Now, this is a study from 1989. I was at this time a professor in the Department of Psychiatry at the University of Maryland School of Medicine in Baltimore. And I was also invited to create a program actually for quantitative EEG, as well as far-field evoked potentials for the peroneal nerve, the median nerve, and auditory far-field evoked potentials, as well as standard evoked potentials to look at, for visual and auditory and somatosensory evoked potentials, to look at the integrity of brain functioning in traumatically brain injured patients. I did this in shock trauma, as well as quantitative EEG. We recorded these various measures in over 1,000 individuals that were traveled to shock trauma. Shock trauma was created by R.J. Cowley, who found a way to help save people's lives by having helicopters travel a radius of about 50 miles to bring people to this one special location in Baltimore, where there is a team of highly specialized and skilled people, nurses and doctors, that would immediately work on these patients to help them save lives. About 70% of the patients admitted have mild traumatic brain injury based upon clinical evaluation of using Glasgow Coma Score and other measures such as post-traumatic amnesia. Dr. Fred Geisler was the chief neurosurgeon at this time. The head of the department was Dr. Michael Salkman. They formed a very good team, and Dr. Geisler played a very important role in the development of this study, which here we're looking at 608 mild head injured patients and 108 age-matched normal subjects. And we did cross-validations of various types to see how well we could separate or distinguish mild head injury patients from normals. And the purpose of this was not to do diagnostics, but rather to evaluate by certain hypotheses about rapid acceleration, deceleration forces that are imparted to the brain in most traumatic brain injured situations. For example, there are shear forces where the gray and the white matter move at different rates. That results in, you can see down here, diffuse axonal injury, as General Rowley was able to show with CT scans and MRIs. And essentially there's a swelling of the axons because they're stretched, and if they're stretched too far, they break. And that's one source of effects on the clinical presentation and the ability to function. In addition, there are contusions to the frontal and temporal lobes where the brain is sitting on a bony vault, and it's closest to the temporal lobes and the frontal lobes to the bones. It's pulled away typically from the top of the head. And then, of course, then there's also rotational forces which affect the long distance fibers from the brainstem up to the thalamus to the cortex with the rotation of the brain, and that also is a effect on the conduction velocities of the white matter, like diffuse axonal injury was. So we formed hypotheses that we wanted to measure coherence, which is a functional connectivity measure, as well as phase differences, which is a measure of the conduction velocities, or in milliseconds. You can put it in degrees, but also in milliseconds, between different points on the scalp, and see how they differ as a function of the severity of the trauma and how they change over time. And I'm just going to go down, and you can download this paper. It's on our website at appliedneuroscience.com, and click on articles. This describes the various frequencies. Here's how we calculated coherence and phase, and the various statistics we used. We first did this, shows a breakdown of Glasgow Coma score 13, 14, and 15. If it's less than 13, then it's considered, it's not mild traumatic brain injury. And our first discriminant function, which is shown here in this graph of figure 1, the normal controls, age-matched controls, were in the light bars, and the black bars are the TBI patients. And we were able to discriminate mild from trauma from the normal controls at 94.81% accuracy. These are the variables that went into the discriminant function. The main emphasis, again, was on conductivity measures, but we also looked at the power, particularly in the alpha frequency band, which, depending on the integrity of the protein lipid molecules in the brain, then the ability of the brain to synchronize neurons to create larger amplitudes goes down. So we had a cross-validation of that discriminant function. Our first cross-validation, independent cross-validation, was 95.4% accurate. And then we did 4 more cross-validations and looked at test-retest reliability at varying times following the admission to shock trauma. So people would often only be there for a few days or a week, and then we were able to call some back a few months down the road, and then see how well they changed their brains as a function of time. And this shows something about the changes over time. We also had collaboration at the University Services in Philadelphia, who ran a discriminative function on a group of outpatients and a small group of normals, and they had 95.2% discriminant accuracy. So essentially what we're able to do is to identify features in EEG that distinguish normal controls from TBI patients, and the strongest loading variables was coherence and phase because of the shear forces, the diffuse axonal injury, etc. After that, I went to the National Institutes of Health. That was at the University of Maryland, 1989. 1990, I went to in Bethesda at National Institutes of Health, become the project manager for the first 128 channel EEG system. I was also part of the multimodal co-registration team, where we would co-register MRIs and PET scans and SPECT scans and diffusion, and then EEG and MEG, as well as diffusion tensor imaging that came in a little bit later. And we could cross-validate them at very high accuracy. We actually came up with what's called the Daleric Atlas space, and then the Montreal Neurological Atlas space. This is a common atlas, so you can co-register different images. We're able to cross-validate those images quite well. And now that's the mainstay today in science. The EEG sources are co-registered with high accuracy and cross-validated with other imaging modalities, and there's several thousand papers now on inverse solutions of the EEG and the magnetic encephalography. But this was funded here by the Department of Defense and Veterans Head Injury Program. And Dr. Salazar was the head of that. And this was done at the Bay Pines VA Medical Center. And what we did here is we looked at mild, moderate, and severe traumatically brain injured patients from 15 days to 4 years after injury. We had Glasgow coma scores and various clinical measures. And then we wanted to see if we could cross-validate the earlier 1989 paper. And we did, but I intentionally left out power because I was much more interested in connectivity. So this is the same set of variable set, but without power or amplitude. We had neuropsychological testing of all of these individuals. We again calculated coherence and phase and coherence and phase differences. This is the breakdown of the subjects. And we had a training set. This is a list of the connectivity measures. And this shows you the classification accuracy, which is 96.39% discriminant accuracy, separating the mild from the severe traumatic brain injury patients. And this is the distribution, mild versus severe. This illustrates more or less where the connectivity is, the measures that were entered into the discriminant function, both cross-hemisphere and intra-hemisphere measures. These happen to be the highest loading t-tests. We found that we could correlate the loss of consciousness with the discriminant function at 0.561 accuracy. Correlation is highly significant at 0.001. And the Glasgow Coma score is minus 853, which is highly significant. That is, the QEEG was cross-validated with a clinical measure that measures the degree of consciousness deterioration, separation from a Glasgow Coma score 13. Actually, this went down to Glasgow Coma score 5 to 8 or so. 3 is the lowest. That's when somebody's in very deep coma. I think these were from 4 to 15. In any case, we're able to correlate the discriminant function with the severity of the traumatic brain injury. We also did a whole series of neurosite tests, the WACE intelligence test for scaled scores, the Boston naming tests, the word fluency test, the attention trails attention test, Wisconsin card sorting test for executive functioning, the Wechsler memory scale, and the California verbal learning test were among some of the tests that were administered. The Neurosite test actually took 2 days of testing, and it's really quite exhausting for these poor individuals. But we got highly significant correlations with the discriminant score. Now, I should mention that we did a factor analysis on all of these Neurosite tests, and we found that 3 factors could account for roughly 90% of the variance, because there's a lot of redundancy in Neurosite tests. And Neurosite tests, the ability for people to respond accurately to a Neurosite test depends on the tester-testee personalities, how they interact with each other. It depends on whether somebody's tired or not. And there's a lot of factors like that that go into the variability of the Neurosite test. Whereas just 5 minutes of eyes-closed EEG it doesn't make too much difference as long as people are alert and it's not stressful. So that's what we use to correlate with the neuropsychs. And then we computed a severity index based upon the discriminant score, and we cross-validated the discriminant score by taking the moderate subjects and seeing where they would lie up, or where they would position themselves with respect to mild and severe traumatic brain injury. And sure enough, they were halfway between mild to severe, indicating a linear relationship between the severity of the traumatic brain injury and the discriminant function scores, or EEG. We looked at a lot of different places. Here are 4 VA hospitals for in Minneapolis, Tampa, Richmond, Virginia, Palo Alto. I was coordinating the data would be sent to us at the Bay Pines VA in Florida. We would get MRIs, the neuropsychs, and the quantitative EEG. And then we also looked at active duty military individuals with traumatic brain injury. Texas was the Air Force, Walter Reed was the Army, and San Diego was the Navy. And we could see what the discriminant scores were generally, and we found typically the active duty military individuals who happened to be a bit younger had less severe injuries. And we did other neuropsych tests. And then we created this severity index. This is actually available in NeuroGuide today, the discriminant function and severity index, where you can essentially predict what the severity of the injury was at the time that the injury happened, even though it could have been 2 or 3 years. We went up to 4 years post-injury, and we could predict, because the Glasgow Coma score was measured at the time of injury. And so we could predict the Glasgow Coma score at the time of injury with EEGs that were obtained 3-4 years later. And so that's one of the interesting things about the severity index. So that's published and available in the literature. And also it's the Journal of Neuropsychiatry and Clinical Neuroscience. This also can be downloaded from our website at appliedneuroscience.com. Now, the finding at the Bay Pines VA, and there's one more that I need to bring in, was interesting in that what we found initially was this study where we looked at the MRI of traumatic brain injured patients. We also evaluated, this is at the University of South Florida. I was a faculty member there as well as at the Bay Pines VA Medical Center. And we found that the gray and white matter distribution in MRIs differed between normals and people with traumatic brain injury, with both 3 millimeter and 5 millimeter slices. We did segmentation of cerebrospinal fluid, white matter and gray matter, and then we developed shape descriptors to look at if you look at the intensity of the pixel histograms of gray and white matter for each subject for different slices, these are 3 millimeter and 5 millimeter slices, as I mentioned, you can then create graphs and use kurtosis and skewness and other methods to evaluate the distributions of the pixel intensity with T1, T2, and proton density. This is an example of a slice. These are landmarks, so we could line up the slices. So we got consistency across slices. And then we created intensity histograms. And this, for example, is a normal subject where this is the pixel intensity of white matter. And this is the pixel intensity of gray matter. You can see they're clearly different. In these images, this is proton density, but gray and white matter can be seen in here as well. And there's a lot of examples of that with an MRI. And then we I calculated the first derivative of this histogram. You can see there's a positive peak as you go up on the white matter to its maximum, and then it falls and you have a negative first derivative, and then you have another positive first derivative for the gray matter peak. Now, in C and D, this is a traumatically brain injured patient. Notice that there is no bifurcation or separation of gray and white matter. It becomes unimodal. And the first derivative has only one peak that goes up. You don't have a second positive peak because there's no separation. Here's the calculations for skewness and kurtosis. So we compared derivatives as well as shape descriptors of skewness and kurtosis between mild and traumatically brain injured patients. And we found, this is an example, the two columns on the left is a normal subject. The rows are slices in the MRI from deep in the brain going up to the top. And the third and fourth columns are two traumatically brain injured patients. And you can see the bimodality in the normals that's missing in the TBI patients. This indicated to us that there was a breakdown in the protein lipid molecules, the integrity of the protein lipid molecules. So more water was flowing more freely in the brain of the TBI patients, and it wasn't segmented or separated well in the TBI patients compared to normals because of the structural integrity. There's reduced structural integrity. And this was consistent with our EEG findings because this indicated that the molecular basis of the EEG, which is really membrane integrity with ionic channels that open and close, and that's an ions flow that creates the electrical field, the EEG, that there's a reduction in the integrity or the efficiency of the molecular mechanisms of action potentials and synaptic potentials, which helps explain why the EEG is so highly different between TBI and normal subjects. Those are the hypotheses we were forming at that time. And we looked at the differences at different slices for different peak areas. The skewness, for example, was significant, really, a slice 3 through 7 with 9 slices in the MRI machine. and kurtosis had a different view of it. That's the peakedness is different, but they're highly significant. We then colored the pixels in the slices based upon their unimodality. And you can see there's some in the normal, but there's a lot in the TBI patients. And so we also looked at the separation of these tissue spaces. In the normals, there happens to be 3 normals. You can see there's muscle, there's white matter, gray matter, and cerebral spinal fluid. It's really clearly separated. Whereas in the TBI patients, they're all smashed together. Cerebral spinal fluid, gray matter, white matter are hardly separate in the images. So there's a breakdown in the integrity of the protein lipid molecules, resulting in an inability, a partitioning of the water in the brain. And what the MRI is looking at are protons in the brain, and the water. And so the macromolecular environment is different than normals. And we compared then T1 proton density to T2, and we found that T2 relaxation time separated both gray and white matter normals from TBI patients the best. So you got really good separation with T2 relaxation time. And so we decided to explore what's going on with T2 relaxation time. For those of you that are not familiar with the MRI, essentially what happens is you put your head into a magnet, and the magnetic field is actually stronger at the tip of your head than it is at your feet. There's a gradient. And protons will line up in the magnetic field, and they'll spin like tops. And the rate of rotation in the magnetic field depends upon the strength of the magnetic field. That's called the Lamar frequency. So you tip of your head is spinning a little bit faster than the bottom of your head, and that's how you get different slices. Now, what happens is when you're in the magnet and your protons are spinning like tops, there's a wire cage, it's called a head coil, around your head, and in that there's small wires, and a brief radio frequency pulse is delivered to around your head, and what that does is it knocks the tops that are spinning, knocks them down, so they start spinning in the plane of the x-axis. So typically, if you imagine a top that's up in the y-axis and it's spinning, it then gets knocked down to the x-axis. It spins at the same rate, but now it's spinning in the plane of the x plane, and then it slowly comes back up to where it was before it got knocked down. If you put a glass of water in the MRI machine, it takes about 5 seconds, or actually minutes, for the water protons to come back up. If you put macromolecules or metal or anything like that in that glass of water, then the relaxation time would be very short. It could be a few milliseconds. So the greater the macromolecular environment and the integrity of that macromolecular environment, then the shorter the T2 relaxation time. The more water there is in the brain, then the longer the T2 relaxation time. So we decided to evaluate that, and this is published in Neural Image in 1998. So we went further, given that finding of there was no EEG in the previous study, it was just MRI, and we wanted to look what is the relationship between the amplitude of the EEG and the integrity of the protein lipid molecules is measured by T2 relaxation time. That hypothesis was initiated by that previous study I just showed. And so we calculated here's the slices. These are 3 millimeter slices. It's a 1.5 Tesla, or it's a 3 Tesla MRI. And this is called the Bloch equation. This is how you calculate the T2 relaxation time. Bloch received a Nobel Prize in the 1950s. We cite his paper in 1946 on how to calculate T1 proton density and T2. That's used in those days for nuclear magnetic resonance. But it's a very foundational equation, but it allows you now to calculate the teacher relaxation time, which is in milliseconds. And what we found is here's the teacher relaxation time in the bottom row for white matter and gray matter. This is the distribution of the teacher relaxation time and all the voxels that you see up here. The yellow is the longer teacher relaxation time. Here's 80 milliseconds. For gray matter, it goes out to 160 milliseconds, 150 milliseconds. The reason for that is that white matter has a myelin in it, which repels water. It's hydrophobic, whereas gray matter does not have myelin in it, which is a fat molecule that expels water. And so you have longer teacher relaxation times in the gray matter than you do the white matter. That's one of the ways you segment the brain. We found that the longer the teacher relaxation time, then the lower the amplitude of the high frequencies in the EEG. We found this in all the subjects. And we did it across subjects as well as individuals. And you would see in different places that we do this, but primarily this is group data. And so you can see consistently, the longer the teacher relaxation time, the lower the EEG amplitude. We also found the longer the T2 relaxation time, then the higher the delta frequency. So there's a shift in the frequency. So the ability of the brain to oscillate at high frequencies, it depends upon the integrity of the protein lipid molecules. So you have ionic channels opening and closing, and the ability of neurons to synchronize at high frequencies. Because the tissue space is compromised mechanically by this force that goes through the brain, there's also a counter-Q component to traumatic brain injury. So if you are hit on your right occipital region, then a force will go from your right occipital region all the way to your left frontal and bounce off and come back. And then you'll see the contra-Q, where that force, because your brain banged against the skull some distance away, as well as the point of injured at the point of impact. All of that you can see in the quantitative EEG, and was seen in that first study I showed you. And so we found that the lower frequencies are higher. This shows some idea which electrodes were most significant, delta and beta. This correlated different slices with the T2 relaxation time and EEG correlation. So it's positive and negative depending on the frequency. So we also looked at neurosite functioning. We found that the longer the T2 relaxation time, then the lower the digit span, or the lower your performance is on the California Verbal Learning Test or the Boston Stimulus Cues Test. In fact, all of the neurosite tests would decrease in the values that the integrity, or at least the cognitive and perceptual functioning of the brain is correlated with the T2 relaxation time, where not only is there a distortion of the EEG and because of the integrity of the protein lipid molecules, but performance on neuropsych tests go down as well. This is digit span. We correlated beta with digit span. So if you have normal EEG, you have good scores on your neuropsych tests, particularly the higher frequencies. The higher frequencies, as I mentioned, are more difficult to generate. This is an equation that we were able to put together to show how the frequency spectrum, the amplitude, is really made up of two compartments. And I won't go into the details of that, but it's similar to the two-compartmental model of coherence that Paul Nunez developed and that we cross-validated independently, where the gray and white matter, where essentially what's going on, the connectivity of neurons, the local connectivity drops off smoothly as a function of distance. It's an exponential decrease, logarithmic decrease, whereas the long-distance connections have an increase in coherence at longer distances wherever the termination of the fasciculi are. That is, for example, the frontal occipital fasciculus is a long-distance fiber system. Well, as you get close to the terminal points of that long-distance fiber system, coherence goes up, because coherence is equal to the number of connections times the strength of the connections. And so we're able to model this in terms of the severe TBI, normal and mild, and the gray and the white matter with local processing and long distance connections are both involved in this. We then asked the question, what's the relationship between the integrity of protein lipid molecules and T2 relaxation time and EEG coherence? And this is the same equations we had before to calculate coherence. This time, though, what we did is we measured coherence in two different directions for the left and right hemisphere. So we go from front to back, that's anterior to posterior. This is FP1 to F3, FP1 to C3, FP1 to P3, FP1 to O1, increasing distance. Or you can go from the back forward, O1 to P3, O1 to C3, O1 to, this is right side, this is F4 and FP2. But you do it for both left and right side because coherence is a measure of it reflects the conduction velocity and the magnitude, as I mentioned, of connections which do decrease in the short distance compartment, but increase in the long distance compartment. Again, we use the Bloch equation for T2 relaxation time. These are various correlations. I won't take my time with it. And we found a difference between short and long distances. They found that the longer the T2 relaxation time, then the higher the coherence. Whereas the longer the T2 in the long distance compartment, 28 centimeters, for example. Whereas the short distance compartment, the longer the T2 relaxation time, then the lower the coherence. And again, severity of traumatic brain injury is related to lengthened T2 relaxation time. Now, this indicated to us a compensatory dynamic. Essentially, the short distance compartment has been damaged, and now the brain shifts to the long distance compartment as a compensatory dynamic. This is also related to what's called the small world model. For example, dynamically organized systems, if you can process your product, let's say in economics, locally, and not depend upon long distance shipping like from Australia or China or something like that, then you're more secure and more efficient if you can process everything yourself or locally. The brain is similar to that. The efficiency of information processing is where most of the processing is happening locally, and you want to minimize the burden on the long distance systems. And so during child development, you actually see a pruning away of the long distance system and a sort of an increase in connectivity of the short distance system. Now that creates, as you get older, a fragile brain, because if there is damage, then it's less compensation. Particularly you see that after about age 6, 7, 8 years of age. It's important for neurosurgeons who don't want to remove tissue in the older children because of an inability to compensate post-surgery. So that's one of the factors that's involved in decisions about surgery. So we found this consistently. You can also see there's the lower frequencies and higher frequencies are two different compartments. This is the long distance, and this is the short distance compartment. And again, we looked at it in going in different directions. This one was posterior to anterior, this is anterior to posterior, and left and right hemispheres are different. There's different packing density in the left and right hemisphere. Essentially what's going on is the back of the head has higher packing density of neurons than the front of the head. And so the rate of decline is different for coherence as a function of distance, going from back to front or front to back. And the long and short distance system is a little different. This is anterior to posterior for gray matter and white matter, showing the two compartments again. And so we did a lot of analyses evaluating this, looking at white matter, gray matter differences. This is the two-compartmental model that Nunez first worked up, then we developed it and cross-validated it. The short distance compartment is like getting a pen, a felt pen, and putting it on some cloth, and you'll see it just diffuses out. So this equation here is a diffusion equation for the short distance compartment. Then the long distance compartment, that's where the long distance cortical fasciculi are. It's made up of a positive component. So as the connections increase in density, or the number of connections, then coherence increases. So it's really made up of two compartments, short distance and long distance, and it helps cross-validate coherence as a measure. Its coherence is related to the neuroanatomy. This study helps give cross-validation to coherence and phase. I got another study for phase, but that coherence, as long as you don't use, scramble the phase up, like independent components analysis does. You just simply look at coherence or look at the phase differences of what comes out of the brain. Then the underlying anatomy, the short and long distance features of the underlying anatomy, and packing density, things like this, synaptic rise times, conduction velocity in the white matter, they all determine the phase delays, the consistency of phase delays, and the magnitude of coherence. So this helps validate the underlying molecular foundations of EEG, particularly connectivity, functional connectivity, as a function of the underlying anatomy itself and the integrity of that anatomy. Now, we then, after doing that study, wanted to go further and see how well we could really nail this down in terms of the modeling and the complexity of the space in the brain, the integrity of the brain, and the way that the EEG spectrum is correlated with the actual molecular integrity of the brain. Now, the MRI is fantastic because it's looking at the molecules, okay, the molecular foundation, and to correlate EEG with the molecular with measures of molecular integrity is important to be able to do. And we were one of the first to do that. This is the standard MRI with T2 relaxation times it did before. Then we do correlations. Generally, we found, again, the shorter the T2 relaxation time, then the higher the alpha. And so what we did here's the block equation again. But in order to evaluate the complexity and the molecular integrity of the gray matter, I decided to compute what's called the Laplacian. That's an equation developed by Simon de Laplace in the early 1800s. Initially, he used that to transform electricity, an electrical field, into currents, or measured in amperes. So the electrical field is in volts, and then if you transform that electrical field spatially, then you will get values in amperes. Essentially, it's got x, y, and z. It's looking at the second spatial derivative in the x, y, and z directions, that is how rapidly is the environment changing. For example, if you have, and NASA uses this, for example, in the evaluation of planets, where if there's a surface in the planet which is like a desert and it's a plane, it's not changing, it's flat, then the Laplacian equals 0. When you come to a mountain where there's this change in the contour of the surface of the planet, then the spatial derivative of the Laplacian operator gets large. So it's a measure of the complexity of the space. So it's a spatial operator, and looking at how heterogeneous that space is. If it's homogeneous, then the derivative equals 0, second derivative. And as I mentioned, if it's corrugated, rough bumps and things in it, then the Laplacian is larger. And we found, we correlated current density as a function of the had different correlations with frequency of the current density. And then we looked at the second spatial derivative. I'm going to particularly look at this side because this is the second spatial derivative of T2 relaxation time. And basically, this is the T2 relaxation time here. This is the second spatial derivative of that. And the more complex the brain, then the higher the amplitude of alpha. Now, this is T2 relaxation time, as we showed before. The longer the T2 relaxation time, then the lower the amplitude. but this is spatial complexity. So you have both the integrity of the protein lipid molecules being diminished by traumatic brain injury, which is characterized by an increased amount of water, which means the second spatial derivative is going to be small. So we can quantify that. We looked at this as in different places, different slices, and different frequencies. And we correlated the second spatial derivative with WISC-R, and where the more complicated the brain, the better the performance on the Neurosite Tests. Word fluency, better on word fluency, the more complicated the brain is, and where it has not broken down and become homogeneous with water flowing, and that's what created initially the finding I first showed of the MRI being unimodal. This explains what's going on there. It quantifies it in more detail. And then the same thing with the power. The more complicated the brain, then the higher the power. We did a number of different controls. I came up with this model where the voxels of the brain really are made up. This is a single voxel of a whole, I'd say, 1 million neurons. These are 3 millimeter by 3 millimeter by 3 millimeter, and, or 1 millimeter by 1 millimeter by 1 millimeter, where I take the Laplacian and it's proportional to 1 over T2. And this factor here, lambda or sigma, is a coefficient that will change depending upon that relationship between the two. And you can model it also. Imagine the brain is made up of a bunch of circuits, a bunch of loops with information flowing between, let's say, the thalamus or the cortex back to the thalamus or cortical loops. And there's a huge number of loops. So you can model the transit times in the loops and the generation of current in those loops by this resonant circuit where you got capacitance, inductance, and resistance, or conductance, the inverse of resistance, and then we can create a transfer function. This is the amplitude of the alpha rhythm that varies as a function of the T2 relaxation time. And now this is the transfer function that comes from this model up here. And what we essentially argue in here is that if there's a lot of synaptic input into the molecular environment of the brain, and based on the T2 relaxation time and the of that volume, then that predicts the scalp EEG spectrum. So the MRI predicts the scalp EEG spectrum, and it turns out this is reversible. If you know the EEG spectrum, then you can predict the MRI T2 relaxation time. They are correlated, significantly correlated, as we've shown repeatedly in these studies. I went a little bit further. I've always enjoyed physics, and I started as a math major, actually, and then a physics major as an undergraduate. I eventually graduated as a chemistry major. I'm not going to go through the details of these equations, but these are standard equations you get in first-year college physics on electricity. And these are the coefficients for the transfer function, but we're able to come up with this concept of REEG, which relates the integrity of the protein lipid molecules to the amplitude of the EEG. So we're able to do that as a transfer function itself. And see, I wanted to see if we got one more in here. Show the relationship between source localization. That's not it. And the localization of those sources that you can find in the, well, here it is. Whoops. This was published when I was at the National Institutes of Health as the 128 channel project manager for EEG and putting these things together. This is a voluntary finger movement, arm and thumb movement. We can measure the movement of the potential is produced when you move your thumb. This is before your thumb moves. This is the intent to move. And then this is after you move your thumb. These are the dipoles we could measure. The dipole number 3 is the cingulate gyrus or supplemental motor cortex, and this is the somatosensory cortex, left and right hemisphere. And then we could calculate a time series based upon these dipoles, pre and post, and this is a standard procedure, and then see how the dipoles change before and after you move your thumb. And you can see this is coherence, instantaneous coherence using joint time frequency analysis between these dipoles. I'm not going to go into the detail of these as phase differences. Suffice it to say there's a switch where there's high coherence before and then it shifts and returns to what it was before. So there's this switching. And actually what's going on is when you move your right thumb, you're inhibiting your left thumb. You move your left thumb, it inhibits your right thumb. That creates bimanual coordination. And we're doing this all the time. We're alternating left and right. You can move together, but it's faster if you shift left and right. And then finally, I just wanted to show the dipole for the dipole number 3, supplemental motor cortex, and the PET center they were within 5 millimeters. So there's this cross-validation of the sources of the EEG to PET scans. And again, there's a whole lot of science in that area. And finally, I'm going to show the new advances in EEG, where now you can compare an individual to a age-matched normative database. This is a person who was injured in the right parietal region. It's significant C4, P4, T4, T6. And then you can launch the Neuronavigator and look at the 5 hertz where he was significantly deviant from normal. We'll pick one of the networks. I'll just look at Parkinsonism. See if that did it. And then we'll look at get rid of the cortex. We'll look at connectivity and put in the center voxel. And now evaluate the relationship between the cerebellum and the sensory motor cortex. This is the vermis and red nucleus, subthalamus, etc. So now you can do this because Ernesto Soler was able to solve the inverse solution and smooth it and create essentially a magnetic solution to the inverse, electrical inverse. The gray matter, white matter, cerebral spinal fluid, and all that heterogeneous space inside the brain is invisible to magnetism. It does not interfere with magnetism, whereas it does interfere with the accuracy of source localization for electricity. So what Ernesto Soler did is he found a weighting function called single value decomposition. That's Roger Penrose's famous equation. He applied that to the solution, and so that the lead field, I won't go into details of that, but the lead field becomes homogeneous for electricity, just like it is for magnetism. As a consequence, you're able to see deeper areas of the brain that you're not able to without that method. And finally, we have a new release where we can get statistics, go to statistics, Navistat, and I think Navistat has been launched already. And there's Navistat. I loaded in these 2 individuals, and this is pre and that's post treatment, for example. That's coefficient of variation, but we can look at the means. And you can see the area that's deviant from normal there, and we can do an independent t-test. You can do screen captures of this, put it into the patient's folder, allow see how the patient's brain changes as a function of treatment, and you can expand any of these that you wish. and contract them. And there's a number of different t-tests. Coefficient of variation is available, percent deviation, absolute differences, etc. All of which you can then export as a tab-delimited file that you can then, so it's got the p-values or the t-values, whichever one you want, and you can then do more statistics. You can do both group and individual statistics. So this is a powerful tool. It's similar to the Neuronavigator, except we'll have in here all the connectivity measures that the Neuronavigator or the current Loretta statistics does not have. It just has the currents, and you can also then with the Neuronavigator look at diffusion tensor imaging, as long as this doesn't crash. And those of you that have used the Neuronavigator, you're probably all familiar with this. So that was the presentation I made at the Society for Brain Mapping and Therapeutics. And so I'm going to thank you for watching.